Hello, everybody. So this week, we're going to talk about field extensions and absolute values. Let me just start by recalling something that's come up before. It's kind of important. So, example, let's look at a number field. So find an extension k over q. If I have a finite extension, I can write, well, okay. If I have a finite extension, I can always write k is equal to q adjoint alpha for some primitive element alpha by the primitive element theorem, which is isomorphic to q of x mod f of x, where f is the minimal polynomial of alpha. Okay, and well, sort of one thing that's sort of useful to do is to tensor this expression with the real numbers. So tensor my field k with the real numbers. So this came up, for example, when we were proving in various things about rings of integers. And so and this creates some real vector space with the same dimension, of the dimension equal to the degree of k. And this vector space, k tensor of qr, this is sort of the vector space where we made all of our arguments of lattices to sort of understand that a ring of integers okay, and like ideals and the class group. Okay, so this is pretty important. And what made it sort of accessible and useful is that on the one hand, sort of this contains the ring of integers, the lattice. But on the other hand, it also sort of has some simpler description, which is just the product of, this is isomorphic to, what do we, r to the r times c to the s, where r is the number of real embeddings and s is sort of half the number of complex embeddings. And the reason for this was sort of f of x factors in sort of r of x. So if I look at sort of this presentation as q of x mod f of x, well, f of x factors in r of x into a product of sort of linear terms. So this is sort of product of linear terms are linear terms and sort of s quadratic terms. So these are irreducibles. And sort of all these things are distinct. And well, sort of these give you the real embeddings. So you get sort of q of x mod f of x is just isomorphic to sort of product of q of x by the Chinese remainder theorem. Sorry. So q of x, right this way. So k tensor q of r, this is sort of isomorphic to r of x mod f of x. And this is, let me sort of break it apart into enough steps. So this is isomorphic to q of x mod f of x tensor r, which is isomorphic to just r of x mod f of x. And then sort of Chinese remainder theorem, you get sort of a product over all these different factors. And sort of each factor here is just isomorphic to R. So modding out by a linear polynomial, I haven't changed anything. I just have R again. And so there's a unique isomorphism, you just have to send X to lambda I. So one of these lambda I's in particular is alpha. Sorry, ignore that sentence. What I just said doesn't make any sense. But right, so you have to send sort of X to these lambda I's. And okay, and so each of these factors is one dimensional, so this gives you the R to the R. And then each of these is isomorphic to the complex numbers. To get a specific isomorphism, you have to sort of choose a root of this polynomial, which is sort of the same as giving an embedding into the complex numbers that doesn't factor through R. So that gives you your C to the S coming from these terms. Each factor is isomorphic to C. And so here, I mean, this R to the R part is sort of completely unambiguous, but this C to the S part, like you sort of, for each coordinate, you have a choice of sort of taking embedding or its complex conjugate. But okay, that's fine. Okay, so and this was a really useful thing to do. Okay, and so, well, what we can do now is, I mean, somehow this is useful because, well, it's useful because extensions of the real numbers are simpler than extensions of rational numbers. Like, in fact, there's just two of them. There's sort of the real numbers itself and then the complex numbers. And so that let us sort of get some information about this extension of the rational numbers using sort of something we can understand more simply. And we want to do this now with the p-adic numbers too. So, so continuing the example, something new. So again, we have sort of K over Q, a finite extension. Well, it will turn out that if we sort of take this thing, we sort of tensor it with QP instead of with the real numbers. So in real numbers, we got just by sort of completing for the Archimedean absolute value, but we could also sort of compute Q for any p-adic absolute value and see what we get. Well, it turns out this is going to be the product for all sort of primes P in all primes P in the ring of integer that divide P of the completion of K sort of for the absolute value defined by P. So this is the completion. K sub sort of fact P is completion for the absolute value defined by this prime ideal P. So remember, that's sort of just like the order of vanishing along that prime ideal. Sort of that gave you some absolute value. You can complete this field for it. I mean, somehow, okay, so we're not going to prove this fact totally today, but we'll come back to it next time. And the reason this is sort of, okay, so if we look back at this previous example of the Archimedean place, like the reason we got such a nice simple description was because we knew sort of, well, there's only sort of a single degree 1 extension of real numbers itself, and a single degree 2 extension, the complex numbers. Something not, and the p-adic numbers aren't going to be quite that nice in the sense that they're sort of not going to be sort of just like, there aren't just 2 extensions of the p-adic numbers. But however, it will turn out that like there are only finitely many extensions of the p-adic numbers sort of when you fix a degree. So like there are only finitely many extensions of Q2 of degree less than or equal to 5. Like you saw last week, sort of there were only finitely many quadratic extensions. That's sort of one of the problems of the worksheet. So and even so it's not quite as nice as the real numbers, but somehow like you're going sort of from sort of infinitely many possible extensions of Q, sort of, or there are infinitely many quadratic extensions to sort of only finitely many extensions of QP. And then, well, so we'll have to sort of say a little bit more about what these can look like, but already sort of this is sort of interesting. Okay, so I mean, somehow you'll get this, and you'll get these extensions the same way, like you sort of just sort of, to get KP, we're just gonna factor sort of f of x in QPX. So instead, and f is irreducible. Yeah, so here f is the minimal polynomial of some primitive element. So f was irreducible over q, but it might not be irreducible over qp. And sort of each factor sort of is going to give you some field extension. And well, this is almost the same as what I've written here, except sort of I'm identifying those field extensions with being completions at some prime. So this basically boils down to the fact I said last time. So this generalized version of Ostrowski's theorem, that sort of every absolute value either comes from on K, either comes from embedding to a complex numbers, or from a prime in the ring of integers. But I didn't fully justify it last time, and so I haven't sort of fully justified this statement. But we'll come, and this is for now, this is motivational, but we'll come back to this next week. But and somehow this motivates the study of extensions of QP. Or sort of more generally, of non-Archimedean fields. So here, non-Archimedean fields, that means complete with respect to a non-Archimedean absolute value. So examples were QP, and soon we'll see any finite extension of QP satisfies this. FP, percent T. Okay, but then there are many more. Yeah, I mean, somehow, if we want this presentation to be useful, like we should sort of understand sort of what these things look like and sort of how they can use them. Just like sort of this sort of presentation was useful because we understand the real numbers, we understood the complex numbers. Okay, so that's sort of where we're going today. So let me state sort of a big result, and I'm not going to prove it, but I'll say something about the proof. So this is sort of the most important thing. So if K is a non-Archimedean absolute field, so again, this means sort of it's complete with respect to a non-Archimedean absolute value, and L over K is finite extension, then I can define the following. I can define an absolute value on L using the formula. Just take the norm from L down to K. I take the absolute value. So now that gives me some element of K. So I take the absolute value on K. And then I sort of just take this to I take a root. So the L to the, so I take the degree of extension as a root. So first thing is that this is an absolute value. So it's easy to check this is multiplicative. But it's not, and so you have to do something to check this satisfies the triangle inequality, but it does. So this is an absolute value on L. Step one. And then L is complete for this absolute value. And this is the unique absolute value on L extending the absolute value on K. So the reason this extends the absolute value on K is just because if I take the norm from L over K of something that's already in K, I'm just raising that to the power of the degree, but then I'm sort of taking that same root. So I sort of just get back. So that's why it extends the absolute value on K. But then sort of the non-trivial part of that claim is that there's really only one absolute value extending the absolute value on K. So for example, of course, this is not true if K is not complete. I mean, we saw, okay, maybe exercise, but I mean, somehow, like if you sort of have a quadratic extension, you have a prime that splits, then sort of each of the two primes above that are going to define sort of different absolute values. So we're really using here that K is complete. So that's sort of built into this, what it means to be a non-Archimedean field. Okay, so this is going to be a very powerful theorem. It basically says, let me sort of add a remark. This says sort of algebra over a non-Archimedean field. So algebra in the sense of like studying finite field extension sort of automatically upgrades to analysis. In a sense, sort of, you start with just sort of something defined algebraically, a finite extension, but sort of you have a way, you have sort of an automatic way to equip that finite extension with an absolute value, sort of. So the absolute value is sort of what you do analysis on K, and so that extends uniquely to an absolute value on L. Good. So here's sort of one remark. Let me sort of say another remark. So this is also true for K Archimedean. But somehow it's easy because you can sort of just write that on by hand because we've seen. Okay, so if you did this exercise there was an exercise last week that sort of if you did it and you basically know that the only Archimedean fields are the real numbers or the complex numbers. So Archimedean field means complete for an Archimedean absolute value. So then L is also sort of R or C. And some of the only non-trivial thing, so the only non-trivial extension is C over R. But the absolute value on C is the standard absolute value, which is just sort of the value of Z times Z bar, the real numbers, but to the 1/2. Okay, so this is sort of the standard absolute value on C. And well, actually, it's like the same proof that sort of this of uniqueness works over the non-Archimedean and Archimedean setting. Okay, so this is sort of handled for free. And then sort of the proof, and somehow when you prove that this actually defines an absolute value, you sort of do a different proof for the non-Archimedean setting. Okay, good. Great, but okay, so algebra automatically upgrades to analysis. And this is going to sort of be very powerful. For example, like this will let us talk about like the absolute value of roots of a polynomial. So we'll do some applications in that direction. Let me say something about the proof. So I'll just say, and this isn't going to be a proof, but sort of remarks on the proof. Well, okay, well, the first remark is sort of it's easier for DVRs. So easier if this is a discrete valuation. So discrete just means takes values in a discrete subgroup of the positive real numbers under multiplication, or if you sort of take logarithm, that it takes values in sort of just a discrete subgroup of the real numbers. So you take the additive valuation, you get a discrete subgroup of real numbers. okay, that means a discrete subgroup of real numbers is just sort of a copy of Z, sort of just shifted somewhere. And what that tells you is sort of if this is, so if this absolute value is discrete, I mean, this is the same as saying OL, which is just a set of elements L in L, such that the absolute value of L is less than or equal to 1. So this is sort of what we call the ring of integers for a non-Archimedean field. One of the exercises last week was to show this as a ring, and there are some more exercises about this thing this week. Okay, so this is if and only if this is a complete DVR. So it's complete sort of already, and then it will be a DVR. So the maximal ideal is sort of just things that all have absolute value less than 1, that have absolute value strictly less than 1, and sort of you'll be able to take something of sort of largest absolute value less than 1 by this discreteness, and that will be sort of a generator for this maximal ideal. So that sort of tells you it's a PID. Oops. Okay, okay, in this case, so in particular, if you look at theorem 7.38 in Milne, sorry, I guess I said absolute value on L. I should have been saying absolute value on K everywhere. K is the base field. So theorem 7.38 in Milne does this case if also L over K is separable. Which saying, well, if K is of character 0, that's sort of always the case. So like this, and this includes sort of K equals QP or K, any finite extension of QP. So this is, well, this, so first this includes K equals QP, and then sort of by a second application also includes sort of any finite extension of QP. So good, so this is sort of enough for purposes, and there are just some steps that you can simplify in this setting. And basically you can sort of make some algebraic arguments. Okay, I mean, sort of showing in some other sort of two parts of the argument. So for uniqueness, I should have said this is sort of exercise, will be exercise 7 on this week's worksheet. Sort of treats the general case. Okay, so for uniqueness, and this is really just a very general fact. About topological vector spaces. And sort of somehow uniqueness and sort of completeness sort of tied up in this. So like a norm, and like an absolute value is in particular just sort of a norm as a vector space over this, a fine dimensional vector space over this complete field. And it turns out sort of there's just a unique, so if you have a fine dimensional vector space over a complete field, it sort of has a unique structure as a topological vector space. So again, sort of, and some of this is a different incarnation of algebra automatically upgrading analysis. So if you have a fine dimensional vector space, that's sort of an algebraic object, but if you're over a complete non-Archimedean field, you can sort of automatically equip that with sort of a unique topology as the topological vector space. Okay, and that sort of topology sort of can be given by some norm. And then, okay, so good. And so and this is, and then just sort of using like the soup norm, for example, you can check that this norm sort of makes the field complete, the vector space complete. Good, and that doesn't tell you have an absolute value, because sort of an absolute value would be sort of a norm, a vector space norm satisfying some sort of additional properties to be multiplicative. So you're not quite there, but almost. And let me note that in this proof of theorem 7.38, sort of skips an important point, somehow when you're proving this, yeah, again, so you can, if you want to go through the proof, you can do here, but when you're proving this sort of uniqueness and completeness, like you sort of really do them both at once, and the completeness is sort of an essential ingredient. And you sort of have to do an inductive proof for the general case, sort of bootstrapping off of sort of completeness in lower dimensions to go up. So you don't have to do, it's a little bit easier in the case of a discrete valuation. So this case in Milne, but I mean, you do have to be careful not to just assume it's complete. And somehow, okay, so in this proof of 7.38, like it sort of claims something is Cauchy without sort of explaining why that sequence is actually Cauchy. So exercise 7 sort of include, like I think the first part of exercise 7 asks you to look at this and sort of justify this statement. And you can sort of give like a simple algebraic proof this sequence is claimed to be Cauchy is Cauchy, sort of using the structure you have, but and you really do have to say something. So the issue is somehow, okay, you have to show that sort of you have a topological vector space, then sort of any linear functional is continuous. And sort of this proof in 7.38 sort of implicitly assumes that, but this is something that actually needs to be justified, because I mean somehow this is actually the key point in the whole proof. Okay, well anyway, but good. So that's something about that. And then existence. I mean, it's just sort of some manipulations. So to show this formula sort of actually defines a norm, it's manipulations to sort of get down to a simple sort of, you basically get down to a Hensel's lemma type statement. It's not exactly a Hensel's. It's not. And there are many different forms of Hensel's lemma. It's not one of the ones that was on the worksheet last week, but it's pretty close. And like sort of the actual statement you need is sort of so simple. Like you can just prove it as sort of prove it directly instead of sort of trying to break down the most general statement of Hensel's lemma that you use. Okay, so that's sort of how you prove existence. I mean, the better question is like, how do you get this formula in the first place? Like, where is this formula coming from? And the point is, once you know existence, like once you know uniqueness, like that sort of tells you this is the only possible formula. So the uniqueness implies that this is the only possible. I mean, it doesn't say this formula is going to work, but it does says if any formula works, it will be equivalent. Like this will be the formula. And the point is sort of if sigma, and let's just say we're in the Galois situation, then sort of x goes to sort of absolute value of sigma of x. So yeah, let me say this: if is an absolute value, extending the absolute value on k, then sort of x maps to, okay, so yeah, let me call this sort of absolute value sub 1. Then I can sort of define an absolute second absolute value, subscript 2, by just sort of taking sigma, so taking the absolute value of sort of the conjugate by sigma. This will still extend the absolute value on K. I mean, this will still be an absolute value just because field homomorphisms are nice. It will still extend the absolute value on K because sigma sort of preserves K. And so, but sort of if there's a unique such absolute value, so uniqueness implies so this first absolute value is equal to the second absolute value. So absolute value of alpha is equal to absolute value of sigma of alpha. It's another way to say that. Okay, but then sort of if Galois, then sort of the norm of L over K of alpha is just the product of all its conjugates. Okay, so if I sort of take the absolute values, this is the product of the absolute value of sigma of alpha. But and all of those are the same, so this is just the absolute value of alpha to the sort of size of L over K, which is equal to just the degree. Okay, and then here, this absolute value, and now the norm is something in K, so this is sort of just equal to the absolute value in K. Okay, and then taking sort of this root, I sort of get that the absolute value of alpha has to be sort of the absolute value of the norm, the 1 over the degree. Okay, this is in the Galois case, but sort of in a general separable case, you can argue similarly to say that this is the only possible formula. So somehow, and when you just look at this, it might seem like how would you ever know to guess that this was a thing? But that's not really how you should think about it. You should think uniqueness is sort of a very general fact about topological vector spaces. So you sort of know it's going to be unique, and once you know it's unique, like you can deduce that this basically has to be the formula, and then sort of all that's left to do is sort of check that this really does define an absolute value, just sort of some other trick. Okay, but good. So I think that's all I wanted to say about the proof. But again, you can look at this exercise 7 if you want to work through this more carefully. Well, I guess I did want to say one more thing, just about sort of the DVR case and why it's simpler. Well, right. So for DVR and a separable extension, like you can sort of, if there's one at all, then it has to be given by this norm formula. But sort of there's a simpler way to show there's one at all. So, so in the DVR case, I mean, just use sort of OL has a prime above sort of the maximal ideal in K. So OK has a unique non-zero prime ideal. It's the maximal ideal. And then in OL, here's the just integral closure of K of OK in L. That has a prime sort of lying above this, and then you can sort of just take the sort of the absolute value corresponding to that prime. And that gives you an absolute value. Okay. You could also sort of argue, in this case, you can also sort of argue uniqueness sort of algebraically from here, and also sort of completeness, I already said, sort of simplifies. So, but yeah, you can look at theorem 7.38 if you want more details on that case. You can look at exercise 7 on the worksheet if you want to understand the general case. Okay, good. So let's see what this does for us. So let me sort of say a quick corollary. Well, this was for finite extensions, but like any algebraic extension is a union of finite extensions. In particular, if if L over K is just an algebraic extension, so yeah, let me say this full hypothesis. So if K is a non-Archimedean field, L over K is just an algebraic extension. there is a unique absolute value on L extending the absolute value on K. So an algebraic extension, I mean, that really includes sort of infinite ones, like e.g. K bar, so like some algebraic closure. Now I haven't said anything else. I mean, so the reason this is a corollary is just because an infinite algebraic closure, like an infinite algebraic extension, is just sort of a union of its finite sub-extensions. The previous theorem gives a sort of a unique absolute value on each of those. And so because of uniqueness, like these all agree on intersections, and so they sort of define an absolute value on the entire algebraic extension. And you have to be a little bit careful. I mean, if the extension is infinite, then this won't typically be complete. So it's no longer the truth. Like it's not true that K bar is going to be complete in general. But okay, it still has an absolute value on it. So, and this is particularly useful because so this corollary, or sort of alternately, depending on how you think about just the theorem before, is useful because it says, it tells us it makes sense to talk about the absolute values of roots of polynomials. If I have some polynomial in K join X and K is a non-Archimedean field, well, I can talk about the absolute values of its roots, and that's going to be entirely unambiguous. I mean, to talk about roots, I need to sort of take some algebraic extension where there are roots. But somehow the point that there's not only does there exist an absolute value, so that sort of gives there exists an absolute value, that tells you sort of once you sort of pick an extension, you can talk about roots. But the fact that it's unique tells you it doesn't sort of matter which extension you pick. Like sort of picking different extensions, like there are going to be sort of maps between them, but sort of it's not like roots in one extension aren't the same thing as roots in another extension, but somehow their absolute values always agree. So it doesn't matter where you do your computations, sort of absolute values always agree. And so it makes sense to sort of start with a polynomial and talk about the absolute values of its roots. Excuse me. Okay, so this is going to be a pretty powerful thing. Let me give a couple of applications of this idea. So let me sort of state one result. Yes, we can talk about Krasner's lemma. I'm going to give two versions. So the first one is going to be sort of a non-standard version, but I think it's sort of more useful than most of the standard version. Sort of as something to keep in your head. Okay, so this first version says, if K is a non-Archimedean field, and again, just keep in mind QP if you're getting lost, sort of thinking about things. And somehow this is already very interesting when K is QP. And F in KX is separable, then for any G in KX sufficiently close, meaning all of the coefficients are sort of sufficiently close. So it means there's sort of some small neighborhood of the coefficients, where sort of all the coefficients of G are in that neighborhood. So for topology of the coefficients. Each root sort of alpha I of F sort of in any algebraic closure. So let me pick some algebraic closure. So for each root alpha I of F, there is a unique closest root beta I of G to alpha I, so closest to alpha I. And so these two roots generate the same extension. So for example, this implies like if F is irreducible, then G is irreducible. So sort of that's sort of some weak thing applies, but it's much stronger. It's saying sort of you look at sort of polynomials whose coefficients are near enough to the coefficients of F, then you sort of can't change the extensions you generate. Okay, but sort of somehow to make sense of this statement, like, and sort of how you prove the statement, you're really using this fact that sort of you can talk about roots. You can talk about the distance between sort of a root of F and a root of G. So you're using that you have sort of some absolute value on K bar. Okay, so good. Let me state the proof of this. Let me outline the proof of this. Well, and you just use sort of the Newton method version of Hensel's lemma. So this was on the worksheet. This is sort of the strong version of Hensel's lemma for roots. And somehow you could start with F, and then and sort of the key point is if you look at sort of F prime of alpha, so if alpha's root, then if I look at F prime of alpha, this is sort of just the product of alpha minus. So I look at F prime of alpha I, this is sort of alpha minus the product of alpha I minus alpha J. So that's a simple exercise on differentiation if you haven't done this. But so somehow controlling like how big the derivative is, which is sort of what matters for this Newton's method, is so controlling how big this derivative is sort of the same as sort of controlling like how close you are to sort of these roots. Okay, so I think yeah, and it's okay. You have to be slightly more careful in this, but and somehow okay, you have to work out the details, but that's some other point. So you can the distance between roots sort of shows up in the derivatives. Okay, and then so and what you're going to do is sort of you're going to say sort of okay, if G is sort of close enough to F, like then sorry I haven't changed the derivative. Like if I sort of so you want to apply Hensel's lemma, or this Newton method version of Hensel's lemma to G to show that sort of there's a root of G sort of close to this root of alpha, the closest root alpha I. So if you don't change the coefficient so much, and well, you can do it. Okay, good. So that's how this proof goes. Let me say a corollary of this. So if K over QP is a finite extension, then there exists a sort of at least I'll call this L. L over QP is a finite extension, then there exists a finite extension K over Q and a prime P in OK such that the completion of K with respect to the prime P is isomorphic to L, sort of as an extension of QP. This prime P divides P. This prime sort of script P divides this regular P. Okay, and this works more generally than over QP, but already over QP, it's interesting, especially sort of with regards to our original motivation. Our original motivation was sort of based on this idea that you could sort of break up on an extension of Q, and you sort of when you tensor of QP, like you sort of break it up into sort of now extensions of QP that sort of encode some information. So this is sort of going in the other direction. This is saying sort of conversely, like if you have an extension of QP, you can always get it in this way. Like it's always sort of coming from one of these completions. And sort of, well, and the reason this is a corollary is, I won't spell all the details, but it's just because Q is dense in QP. So sort of for L is equal to QP X mod F of X, sort of can you find G in Q of X sort of close enough to F to apply the previous lemma. Or the previous result to apply Krasner's lemma. So you just sort of find a polynomial with rational coefficients that's close enough to sort of its roots generate the same extension of QP. And if you think through what that means, it's sort of exactly saying, you think what that means if you compare it to this first example, that's exactly saying sort of there's some prime of K. So you take K to be Q of X on G of X. And in fact, sort of in this case, sort of K tensor QP is going to sort of just be there's only be one prime above P. So it'll be this one. Okay, good. Yeah, okay, good. So that's sort of, okay, that's one nice example. Let me, right, there's a different version of Krasner's lemma that I should state. Yeah, so another nice example is like, for example, you can prove that if I take like an algebraic closure QP bar of QP, well, that's not going to be algebraically closed, it turns out, but you can take its completion. And then Krasner's lemma lets you show that that completion is algebraically closed. So that's one of the exercises on the worksheet. And this is another good application of Krasner's lemma. Let me sort of say the traditional version of Krasner's lemma, from which you can deduce the version I said above, but somehow I prefer to deduce that version above using Hensel's lemma, the Newton approximation. And they're pretty closely related anyway. So this says, okay, so K non-Archimedean, K bar, algebraic closure. Then I have alpha and beta in K bar, and alpha is closer to beta than to any conjugate of alpha. So like to any sort of sigma of alpha. So or to any other root of its minimal polynomial. So alpha is closer to this root, to this number beta, than it is to any conjugate of alpha. So any other root of its minimal polynomial over k. And I should require alpha is separable over k beta. Okay. Well, then the statement is that the field generated by alpha is contained in the field generated by beta. Somehow you can get to alpha from beta. Okay, so again, sort of, and this isn't say in terms of polynomials like the other one, but in the polynomial is hidden in the sentence like alpha is closer to beta than to any conjugate. So in alpha is closer to beta than it is to sort of any root of its minimal polynomial. And then you're saying something about sort of one field being contained in another. And okay, so if you sort of think a little bit, you can upgrade the statement to the statement of the previous version. And well, one nice thing about this is the proof is like one line. So you should, in some, I'm going to leave it as an exercise, that one line, but just consider embeddings of sort of k alpha beta into k bar that's sort of fixed beta. So in sort of by Galois theory, you just need to show that each of these, by Galois theory, you just need to show that each of these sort of sends alpha to alpha. Well, this condition on the absolute values and the fact that sort of like the absolute value of sigma of alpha, the absolute value of sigma of something is going to be sort of the same as the absolute value of the thing, will sort of let you use this condition. Okay, good, but you should think that through yourself. Good. Okay, but again, so I think this is a useful formulation sometimes, but for me, it's always been more helpful, I think, to sort of keep this formulation in my head about sort of roots of nearby polynomials. But pick your poison. Okay, so this is sort of one example of the kind of thing you can do. And we'll give we're going to sort of give one more application of this in a minute after we discuss things. I mean, some of it, I said this statement earlier that there are only sort of finitely many extensions of QP of any bounded degree. And Krasner's lemma is sort of one of the key ingredients. And Krasner's lemma says, like, even though you have sort of super infinitely many polynomials that could sort of potentially generate different extensions, like actually it's not so bad because sort of ones that are nearby each other sort of generate the same extension. So that's sort of one ingredient of the proof. Okay, but before I do that, I want to sort of talk about sort of another topic related to absolute values of roots. This is the topic of sort of Newton's polygons. Okay, and so here it's sort of useful to use the additive version of the absolute value. So let me just sort of say V is going to be, okay, so K is non-Archimedean field. Then V is going to be the log of, I'll take just log base E, but you can take log base anything, and the same, so everything would still work out. Log of absolute value. So this sort of turns multiplication to addition instead of turning multiplication to multiplication. in like when sort of it's discretely valued, so you usually want to take sort of a specific choice of the base, and then so that like the image is really just Z. So yeah, so in particular for like discrete valuations, like this is sort of just the order of vanishing. Okay, so yes, this is okay. Well, so anyway, just for the statement of what I'm going to do next, this will be an equivalent but more useful quantity to work with instead of the absolute value itself. Okay, and then I'm going to look at so f of x is equal to an x to n plus an minus 1 x to n minus 1. Okay, people have different conventions, but I'm just going to do it like this because I think this is what Milne does. Then the Newton polygon is the lower convex hull of the points oh, so I put this is probably backwards somehow. No, does it. Let me do it like this. Okay, and somehow I'm just going to flip my picture, so it's not going to matter so much, but let me do it like this. So this is the lower convex hull of the points. Well, it's going to be a polygon, so it's going to be points in R2. Where I take sort of the x coordinate is just k, and then take the valuation of the kth coefficient. Okay, so in lower convex hull, it sort of just means, well, it's easiest to draw a picture. So example will be well, I don't know, let's take, okay, so k is going to be q2, and we'll take sort of 2 cubed times x plus x squared, or sorry, 2 cubed times x squared plus 2x plus 2 squared times x. Okay, we'll see what this looks like. So plus 2 squared, constant term, sorry. Okay, and then I'm going to plot my points. So the first coefficient, the 0th coefficient, sort of 0, and then my valuation is 3. Then sort of 1, 2, so go from 0, 1, 2, okay. The first, like the next coefficient is 2, which sort of has 2-adic valuation 1, so it's divisible by a single power of 2, so this goes here. Then the last coefficient is 2 squared. Okay, and so it's that, and then the Newton polygon here is going to be sort of the line segments between them. If I look at, so instead of like x squared plus 2x plus 2, then I'm going to get the Newton polygon. So here I have so 0, 0, 0, then 1, 1, then 2, 1. Okay, and here sort of convexity is going to make me have to sort of miss one of these points. So I just draw the line sort of below these. Okay, so, and you can look up what a lower convex hull is, but this picture sort of basically explains it. I mean, you should be sort of getting something that's sort of convex above it. And sort of, you're going to draw some lines between dots and to get the boundary, and sort of just sort of the thing that lies above it should be convex. So somehow if I drew a line here and then a line here, the thing that lies below it should be convex. Okay. So the thing that lies above it should be convex. I had to pause and sort of think for a second. The thing that lies above it should be convex. I mean, somehow, if I drew this and then this, so the thing that lied above it wouldn't be a convex region, precisely because I could sort of draw this line between 2 points that would leave it. Okay, so in sort of another, what you can do is you can you start at the left most point, and you sort of draw these lines like this until you sort of hit a point and then you stop. So I think here would be okay, and then you sort of just keep on doing it. So like here, so I hit this point, and now I sort of start at this point, and I draw lines until I hit a point, and I stop, and I take that segment, and here sort of I was already done. Okay. Good. Okay, but so that's what the Newton polygon is, and why is it useful? Well, it turns out it encodes the absolute values of the roots of the polynomial. So theorem, which you can either do as an exercise or look up in Milne, and it's not so bad, is that there are exactly so the segments of sort of the Newton polygon, these correspond to sort of roots of the same absolute value. Here's sort of the x length of the length along the x-axis of the segment is the number of roots, and the slope is the additive valuation of those roots. So, okay, so in the above examples, here we have 2 segments, each of length 1. So there's 1 root of slope. So 1 root of alpha with v of alpha equal -2, and 1 root beta with v of beta is equal to 1. So this slope is 1, this slope is -2. Okay, great. Well, so in particular, I mean, some of this is an irreducible polynomial. So here we use this sort of key thing that, I mean, that using permutation, like, automorphisms don't change the absolute value. So like absolute value of sigma of alpha is equal to absolute value of alpha. So somehow each of these segments also sort of corresponds to a factor. The factor itself may not be irreducible, but sort of all of the roots of the same valuation sort of give you a factor of the polynomial sort of defined over Q2, like defined over the base field. That's sort of useful. Okay, so similarly here, we just have 2 roots alpha with the valuation equal to 1/2. And so this actually tells you this polynomial has to be irreducible. It's not just because there's one slope. And like if the slope was an integer, there's not just there's one segment. You have one segment with integer slope, then it may or may not be irreducible. Here, though, sort of the slope is 1/2, and this is sort of if we take both these examples, I'm sort of taking v to be log base 2 of the absolute value, the 2 absolute value. So v is sort of really just the power of 2 dividing. Well, but here, none of these roots alpha can be in Q2 because sort of everything in Q2 sort of would give you an integer valuation, whereas here 1/2 is not an integer. So these things are definitely, so the roots of this aren't in Q2, so this sort of quadratic polynomial has to be irreducible. Okay, so this is sort of super useful. Again, then this is sort of just another tool you have in your, like, you have all these cool tools in your belt for like roots of polynomials over p-adic fields and non-Archimedean fields in general, like Newton's lemma and the Cancel's lemma, and like now Newton polygons. To sort of let you sort of quickly say a lot about the roots of a polynomial. And well, and that's a very powerful thing. Okay. Good. So I think I want to say a few things about the discretely valued case. Let me talk about sort of separable extensions. New color. Where the non-Archimedean field is discretely valued. Okay. So, and the big thing to keep in mind is just if k is equal to qp, well then any finite extension is separable. And that's the one that matters most for our applications later. So, okay, so if L for k is finite, separable. So OK equals, this is just the things of absolute value less than equal 1. In fact, OL is going to be the integral closure of OK. So this is an easy exercise. And the hardest part is sort of making sure, the hardest part is probably I haven't been totally consistent in my notation. So here, OK means the things of absolute value less than equal to 1 in K. OL means the things of absolute value less than equal to 1 to L. And okay, and then I'm saying this is the integral, OL is the integral closure of OK, which basically says like this is sort of somehow reasonable notation to use, like compared to what we were talking about with rings of integers before. Okay, so that's easy enough, and that's an exercise on the worksheet. But once you have this, I mean, sort of the general theory, when OK is a complete DVR, this is basically equivalent to saying K is discretely valued. As I said near the start of the lecture. So the general theory of Dedekind domain applies. Dedekind domains and their extensions. In particular, this is okay. So this is not the only way to say it, but somehow this is an efficient way to say things given what we developed, already. And so if P, I think I wrote this earlier as M, this is sort of the maximal ideal. So the unique non-zero prime ideal is maximal. So this unique non-zero prime ideal. So it's unique because this is a DVR, not just a arbitrary Dedekind domain. And just serve, and this is just all the things with absolute value less than 1. But it's a PID, so it's sort of generated by a single thing. So there's and that's such a thing as called a uniformizer. Okay, and then there exists in sort of P factors in OL. But in OL is also a complete DVR. So you can see this, for example, from the formula for the absolute value. So the formula for absolute value was you took the absolute value, you took the norm, and then you took the absolute value in K, and then you sort of took that to the 1 over the degree. So sort of if the absolute value only took discrete values, like sort of this is also just going to take the roots of those discrete values, so it's still discrete. So this, okay, so this is also a complete DVR. And so that means there's sort of, again, a unique prime ideal, and it's sort of going to be things, all the things of absolute value less than 1. And so this is going to be Q to the E. So Q. Cool. Okay. So it's the unique non-zero prime ideal in OL. Okay, and so I know, I mean, OL mod Q is an extension of OK mod P. So the residue fields are extensions, and as usual, we call F the degree of this. So this is the degree of the residue field extension is F, and then the ramification degree is E. And I know, just from the general theory, that the degree of the extension is F times E. So somehow when we were doing the general theory, like we weren't thinking so much about complete DVRs. We were thinking more about, so we were thinking about like, instead of like complete fields, we were thinking about like Q. And then we sort of had lots of primes, they could split into lots of primes. But you know, everything we did sort of still applies sort of to these complete fields when they're sort of their fraction field of a DVR. So okay, good. Right. Okay. So somehow there are two things you need to understand if you want to understand extensions. Okay, you need to sort of understand sort of residue field extensions, and then you need to understand this ramification. Okay, so let me sort of just state two theorems. Okay. Let me state sort of. So first theorem. So L over K is above. There sort of is a unique maximal unramified extension L naught sort of containing L. So max unramified just means L naught over K is unramified. Okay, and so let me just say out loud how you can see this. Well, in something we've seen already, like on worksheets, is that if you sort of take the composite of sort of unramified extensions, that's still unramified. So that's one way to see this. And you just take the composite of all unramified subextensions. That's still unramified. So that's sort of the maximal unramified extension. Okay, and then sort of if it's going to be degree F. And somehow a simpler way is just if you look at the extension of the residue fields, probably it shows. Yeah, it's not. So let me just assume we're in character 0. Oh, sorry, that's not going to be enough. Let me assume everywhere the residue field extension is also separable. So and somehow actually the definition of sort of unramified should be that sort of E, and the real definition of unramified in general is that E is 1, and then the residue field extension is separable. But let me just sort of assume my residue field extensions are separable everywhere from here on out. Okay, okay, so anyway, you have a maximal unramified subextension, and sort of assuming this thing, the residue field extension is separable, then the index is F. And somehow you can just take a, well, just take some polynomial, like take some primitive element for the residue field extension, and there you're using that separable to say a primitive element exists. And then sort of just lift that polynomial to a coefficient, so an OL, and sort of apply sort of Hensel's lemma, and that sort of gives you sort of, or sorry, that polynomial with one with coefficients of OK, and sort of apply Hensel's lemma, and you see sort of that gives you sort of a root that generates that extension. So that's sort of another way to think about it, is you sort of basically build this in Hensel's lemma. Okay, good. So that's sort of one nice thing. And so L naught K is F, and then sort of L to L naught is equal to E, and this is sort of totally ramified. That's sort of what it means to be totally ramified. It means sort of the ramification degree is the same as the index. So, and this is good. So in particular, so you can always split into an unramified extension followed by a totally ramified extension. Okay, so this gives you sort of some nice structure to extensions of discretely valued non-Archimedean fields, because you can always split them into an unramified extension followed by a totally ramified extension. Excuse me. And I guess I should say, in this condition I put in about assuming the residue field extension is separable, like in the most important case, over like when K is QP, well, then the residue field is a finite field, and that's perfect. So all of extensions will be separable, and so this will never come up. So I guess I should have said we can basically ignore that. Okay, good. So in some, if we want to understand extensions of QP or sort of general non-Archimedean field or discretely valued field, we just need to understand sort of unramified extensions and totally ramified extensions. So let me see next theorem. So unramified extensions these are going to be in bijection, I mean, suitably interpreted. Maybe the best way is sort of fix some algebraically closed field to work in, but let me not worry about that. I'm going to be vague and interpret it. Part of the exercise, maybe it's an exercise to interpret this less vaguely. But unramified extensions are sort of in bijection, or sort of equivalent to extensions of the residue field. So separable. So somehow the problem of understanding unramified extensions is the same as the problem of understanding extensions of the residue field, in the sense that sort of, if I have an unramified extension, it's sort of totally determined by the residue field extension. And sort of vice versa, if I have a residue field, like an extension of residue fields, I can always build an unramified extension that sort of gives me that residue field extension. And again, if you want to prove this, well, first you have to turn to a precise statement. That's okay. That's something you can do. And then after you turn to a precise statement, then it's just Hensel's lemma. Hensel's lemma sort of lets you very powerfully move between roots of polynomials, like polynomials over the residue field and polynomials Yeah, okay. Let me not say anything more about that. And we'll come back to some of these things later. Let's say if L over K is totally ramified, then there exists alpha in L such that L is equal to K of alpha. So there's some primitive element alpha. Yeah, let me say this way. Then L is equal to K of pi for any uniformizer pi. That just means a generator of maximum ideal. I.e. something of sort of largest absolute value less than 1. The minimal polynomial of pi, Eisenstein, and conversely, if okay, so what, and the generalization of Eisenstein is sort of the obvious one. The definition of Eisenstein is the obvious one, and polynomial is Eisenstein if sort of all of its coefficients are in all of its not, so it's monic, and then sort of all its non-leading coefficients are in this prime ideal P of OK, and the sort of constant one's not in P squared. Okay, so literally the same definition of Eisenstein you're used to. And conversely, if F is Eisenstein, then Kx mod f of x is totally ramified. So in particular, f is irreducible. Excuse me, of degree. Sorry, and x. So the root sort of x bar just means the image of x in here, so it's sort of a root of f is the uniformizer. Okay, and here the proof is basically just use Newton polygon. And the proof in this sort of one up here is let's use Hensel's lemma. Okay. Let me state a corollary of this. There are only finitely many extensions QP. So for any n of degree less than or equal to n. Let me say this more carefully. This is true of isomorphism. It's one way to say it, but let me sort of say like QP bar be an algebraic closure of QP. N greater than 0, then there are only finitely many L over QP. So they'll only find intermediate extensions of bounded degree, so by n. So this is okay, let me scroll way up to the start. This is related to this sort of motivation we had, where sort of taking K and sort of tensoring with QP, that was supposed to sort of give you something simpler that could give you some insight. So in sort of, well, the thing over here sort of related to the factorization and sort of closely related words we're doing in codes like the ramification and inertia degree, is sort of just the corresponding ramification and inertia degree sort of for these extensions. So that's already something. But somehow, like one thing that was really nice over here in the Archimedean case was that we just had the real numbers and the complex numbers. We just had like two completely explicit things that we could sort of understand, and sort of we understood those well, then sort of like that's all we had to understand, and we could sort of do things over here. I mean, so basically this tells us, like, this result I just said tells us some weak version of that is over here. Like, it's not true that there are like only finally many fields that can appear over here for sort of any K, but it is true that sort of if I fix like the degree of K, if I'm only looking at like quadratic extensions, only looking at cubic extensions, then there are only sort of finally many different fields that can appear here. So in particular, I could like sort of try and explicitly understand each of those, and then like I'd somehow some very good understanding of this whole thing over here. Okay. So that's the corollary. So that there are these only finite many. Well, first you sort of do the only finitely many unramified. That's sort of easy because that's just sort of extensions of finite fields of FP, really. I mean, there's a sort of a unique, and there's a unique extension of FP of degree n for any n, so that's not so bad. And then sort of to get sort of all extensions, you sort of have to go up to one of these finally many unramified ones, and then also sort of take a totally ramified extension of that. And then you sort of apply Krosner's lemma, plus sort of the fact that like sort of Eisenstein polynomials are sort of in sort of OK brackets X, like the space of all Eisenstein polynomials, if I sort of just write down the coefficients, this is isomorphic to like P times P, so the prime ideal, so all the coefficients times P minus P squared. So this is sort of the coefficient of x time minus 1, coefficient of x time minus 2, and so on, all the way up to the constant coefficient. And you can check this is compact. So, I mean, this is closely related to one of the exercises in the worksheet here. But so yeah, this K is sort of one of these unramified extensions here. And then the prime ideal in that ring of integers, that unramified extension is going to be compact, and it's just a product of compact things. Well, so you have to think about why this is still compact too, but I mean, actually your P squared is open and closed. So you're removing an open set. So this will be compact, and then product of compact things is compact. So this is compact. But somehow Krosner's lemma is telling you like there's sort of an open cover where sort of on each open cover, you're only getting, like on each open set, you're only getting finitely many different extensions. And so then, well, you refine that open cover to a finite cover using compactness, and you sort of get all told only finitely many extensions. Okay, good. So we'll stop there, and we'll come back to a few things about this, and really, but more particularly, more about the relationship with like extensions of Q next time. Thanks.